Hello friends, today we are going to learn about the three-phase inverter. The content of this lecture is Introduction to the inverter, types of inverter, three-phase inverter, 120-degree conduction mode and characteristics of the inverter. Introduction. An inverter is an electronic device that changes direct supply voltage to alternating supply voltage. That is, it is the device that changes from DC supply to the AC output. The inverter doesn't create or make electricity, just changes it from one form to the another. DC in is changed to the AC output. An inverter requires no fuel and virtually no maintenance. Again, an inverter is an electrical circuit capable of turning DC power into AC power, while at the same time regulating the voltage, current and frequency of the signal. Inverters are often a good choice for applications that require the main engine to operate at a job site, that is, powering hydraulic systems or air compressors, etc. Types of inverter. There are two types of inverters, single-phase inverters and three-phase inverters. Single-phase half-bridge inverter. Single-phase half-bridge inverter consists of voltage source, two diodes and two thyristors. Here we can see in this diagram that voltage source is divided in V by 2 and V by 2. Here two thyristors TH1 and TH2 and two diodes D1 and D2. Operation of single phase half bridge inverter. Thyristor T1 conducts load voltage is equal to Vs by 2 due to the upper source voltage Vs by 2. Here, when thyristor TH1 is conducting, the waveform the TH2 will be offset and waveform is getting like this. Ig1 only 0 to T by 2 we are getting this waveform, and again when TH1 thyristor TH1 is off, TH2 is on, and we are getting this waveform from T by 2, T is equal to T by 2 to T. Thyristor T2 conducts and load voltage is getting minus Vs by 2. Again, the output waveform of this is from minus Vs by 2 V by 2. Single phase full bridge inverter. This is the diagram of single phase full bridge inverter. It consists of 4 thyristors, 4 diodes and 1 voltage source. Amplitude of output voltage is doubled up, whereas output power is 4 times to that of single phase half bridge inverter. It is the main advantage over the single phase half bridge inverter, that is output voltage getting at the output is doubled up as compared to the single phase half bridge, and power is 4 times. We all know the relation between voltage and power, that is power is inversely power is directly proportional to the voltage square. Here the operation of single phase full bridge inverter. When T1 and T2 conduct, load voltage is getting Vs. Here we have seen that T1 and T2 is conducting. At that time T3 and T4 will be off and the output getting is Vs. Again, when T3 and T4 conduct, load voltage is getting minus Vs. That is, when T3 and T4 conduct, so the circuit diagram will be like this, and the polarity of the load it changes, and we get at output as minus Vs. When T1 and T2 do not conduct simultaneously, if this happens, the chances of short circuit is increases. So here waveform is shown. Ig1 when Ig1 and Ig2 is conducting, this waveform are getting, and when Ig3 and Ig4 is conducting, this waveform is getting. The output waveform is this, from minus Vs to the Vs. Again, 3-phase full bridge inverter. Circuit diagram is shown here. Here Vs supply voltage, DC supply voltage, T1 the thyristor T1, T2, T3, T4, T5 and T6. 6 thyristors are used here and 6 diodes are used. Here 3-phase load is getting here. The output is getting here. 120-degree conduction mode. In 120-degree conduction mode, only two switches conduct at the same time, one upper switch and one lower switch. Each switch conducts for a duration of 120 in one period of 360 of the output voltage. The gating signal for each switch is maintained for 120 degree. There are 6 sub-intervals of 60 each, that is from 0 to 60, 60 to 120, 120 to 180, 180 to 240, 240 to 300 and 300 to 360. The conducting devices at 0 to 60 is T6 and T1. At 60 to 120, thyristor T1 and T2 is conducting. At 120 to 180, T2 and T3 will be on. 180 to 240, T3 and T4. 220 to 300, T4 and T5 is conducting, and 300 to 360, T5 and T6 thyristors conducting. The output voltage VAN is getting 1/2 Vs. We are seeing this diagram that at 0 to 60 degree angle T1 and T6 is on, so the voltage getting at the AN is plus Vs by 2, and at T6 it is minus Vs by 2, because here at the load voltage AN and here at the load voltage BN, so the polarity will be changed and we are getting minus Vs, minus 1/2 Vs. So we are calculated all voltages of AN, BN and CN. At CN we are getting 0 voltage. Here the waveform of 120 degree conduction mode is shown here. Here VA0, this waveform is getting, that is from 0 to 60, 60 to 120, 120 to 180, like this. VA0, VB0 and VC0 are getting the waveform. Again, here we are calculated the first condition. At conducting angle 0 to 60, switch T6 and T1 are on. Voltage across resistor RAN, that is VAN is equal to Vg by 2, and voltage across resistor RBN, VBN is equal to minus Vg by 2. Voltage across resistor RCN, VCN is equal to 0. VAB is equal to VAN minus VBN. That is, again we are calculating VAB, VBC and VCA. So the formula of VAB is VAN minus VBN. Here VAB, VBC and VCA. The VAB is equal to VA0 minus VB0. So we are subtracting VA0 and VB0, getting the output waveform like this. Again VBC and VCA are getting like this. These waveforms are sinusoidal. Characteristics of a good inverter. Now we are seeing the all inverters. The character of the inverter is the power required by its controlling circuit should be minimum. The power required for the controlling this circuit should be minimum. Its output voltage waveform should be sinusoidal. Its gain should be high. The semiconductor device used in the inverter should be minimum switching and conduction losses. its overall cost must be minimum. So, and its working life must be long. These are the characteristics of the good inverter.